In atomic physics, the Rutherford-Bohr model or Bohr model, introduced by Niels Bohr in 1913, depicts the atom as a small, positively charged nucleus surrounded by electrons that travel in circular orbits around the nucleus, similar in structure to the Solar System, but with attraction provided by electrostatic forces rather than gravity. After the cubic model, the plum-pudding model, the Saturnian model, and the Rutherford model came the Rutherford-Bohr model, or just Bohr model for short. The improvement to the Rutherford model is mostly a quantum physical interpretation of it. The Bohr model has been superseded, but the quantum theory remains sound. The model's key success lay in explaining the Red Berg formula for the spectral emission lines of atomic hydrogen. While the Red Berg formula had been known experimentally, it did not gain a theoretical underpinning until the Bohr model was introduced. Not only did the Bohr model explain the reason for the structure of the Red Berg formula, it also provided a justification for its empirical results in terms of fundamental physical constants. The Bohr model is a relatively primitive model of the hydrogen atom, compared to the valence shell atom. As a theory, it can be derived as a first-order approximation of the hydrogen atom using the broader and much more accurate quantum mechanics, and thus may be considered to be an obsolete scientific theory. However, because of its simplicity, and its correct results for selected systems, the Bohr model is still commonly taught to introduce students to quantum mechanics or energy level diagrams before moving on to the more accurate, but more complex, valence shell atom. A related model was originally proposed by Arthur Eric Haas in 1910, but was rejected. The quantum theory of the period between Planck's discovery of the quantum and the advent of a full-blown quantum mechanics is often referred to as the old quantum theory. Origin. In the early 20th century, experiments by Ernest Rutherford established that atoms consisted of a diffuse cloud of negatively charged electrons surrounding a small, dense, positively charged nucleus. Given this experimental data, Rutherford naturally considered a planetary model atom. The Rutherford model of 1911 electrons orbiting a solar nucleus. However, said planetary model atom has a technical difficulty. The laws of classical mechanics predict that the electron will release electromagnetic radiation while orbiting a nucleus. Because the electron would lose energy, it would rapidly spiral inwards, collapsing into the nucleus on a time scale of around 16 picoseconds. This atom model is disastrous, because it predicts that all atoms are unstable. Also, as the electron spirals inward, the emission would rapidly increase in frequency as the orbit got smaller and faster. This would produce a continuous smear, in frequency, of electromagnetic radiation. However, late 19th century experiments with electric discharges have shown that atoms will only emit light at certain discrete frequencies. To overcome this difficulty, Niels Bohr proposed, in 1913, what is now called the Bohr model of the atom. He suggested that electrons could only have certain classical motions. Electrons in atoms orbit the nucleus. The electrons can only orbit stably, without radiating, in certain orbits at a certain discrete set of distances from the nucleus. These orbits are associated with definite energies and are also called energy shells or energy levels. In these orbits, the electron's acceleration does not result in radiation and energy losses required by classical electromagnetics. The Bohr model of an atom was based upon Planck's quantum theory of radiation. Electrons can only gain and lose energy by jumping from one allowed orbit to another, absorbing or emitting electromagnetic radiation with a frequency nu determined by the energy difference of the levels according to the Planck relation, where h is Planck's constant. The frequency of the radiation emitted at an orbit of period t is as it would be in classical mechanics. It is the reciprocal of the classical orbit period. The significance of the Bohr model is that the laws of classical mechanics apply to the motion of the electron about the nucleus only when restricted by a quantum rule. Although Rule 3 is not completely well defined for small orbits, because the emission process involves two orbits with two different periods, Bohr could determine the energy spacing between levels using Rule 3 and come to an exactly correct quantum rule. The angular momentum L is restricted to be an integer multiple of a fixed unit, where n equals 1, 2, 3, is called the principal quantum number, and h equals h, 2 pi. The lowest value of n is 1. This gives a smallest possible orbital radius of 0.0529 nanometers, known as the Bohr radius. Once an electron is in this lowest orbit, it can get no closer to the proton. Starting from the angular momentum quantum rule, Bohr was able to calculate the energies of the allowed orbits of the hydrogen atom and other hydrogen-like atoms and ions. Other points are, like Einstein's theory of the photoelectric effect, Bohr's formula assumes that during a quantum jump a discrete amount of energy is radiated. However, unlike Einstein, Bohr stuck to the classical Maxwell theory of the electromagnetic field. Quantization of the electromagnetic field was explained by the discreteness of the atomic energy levels. Bohr did not believe in the existence of photons. According to the Maxwell theory, the frequency nu of classical radiation is equal to the rotation frequency nu-rot of the electron in its orbit, with harmonics at integer multiples of this frequency. This result is obtained from the Bohr model for jumps between energy levels n and n-k when k is much smaller than n. These jumps reproduce the frequency of the kth harmonic of orbit n. For sufficiently large values of n, the two orbits involved in the emission process have nearly the same rotation frequency, so that the classical orbital frequency is not ambiguous. But for small n, the radiation frequency has no unambiguous classical interpretation. This marks the birth of the correspondence principle, requiring quantum theory to agree with the classical theory only in the limit of large quantum numbers. The Bohr-Cramer Slater theory is a failed attempt to extend the Bohr model, which violates the conservation of energy and momentum in quantum jumps, with the conservation laws only holding on average. Bohr's condition, that the angular momentum is an integer multiple of h, was later reinterpreted in 1924 by de Broglie as a standing wave condition. The electron is described by a wave, and a whole number of wavelengths must fit along the circumference of the electron's orbit. Substituting de Broglie's wavelength of lambda equals h, P reproduces Bohr's rule. In 1913, however, Bohr justified his rule by appealing to the correspondence principle, without providing any sort of wave interpretation. In 1913, the wave behavior of matter particles such as the electron was not suspected. In 1925, a new kind of mechanics was proposed, quantum mechanics, in which Bohr's model of electrons traveling in quantized orbits was extended into a more accurate model of electron motion. The new theory was proposed by Werner Heisenberg. Another form of the same theory, wave mechanics, was discovered by the Austrian physicist Erwin Schrödinger independently, and by different reasoning. Schrödinger employed de Broglie's matter waves, but sought wave solutions of a three-dimensional wave equation describing electrons that were constrained to move about the nucleus of a hydrogen-like atom, by being trapped by the potential of the positive nuclear charge. Electron energy levels. The Bohr model gives almost exact results only for a system where two charged points orbit each other at speeds much less than that of light. This not only includes one-electron systems such as the hydrogen atom, singly ionized helium, doubly ionized lithium, but it includes positronium and Rydberg states of any atom where one electron is far away from everything else. It can be used for K-line X-ray transition calculations if other assumptions are added. In high-energy physics, it can be used to calculate the masses of heavy quark mesons. Calculation of the orbits requires two assumptions. Classical mechanics. The electron is held in a circular orbit by electrostatic attraction. The centripetal force is equal to the Coulomb force. where m is the electron's mass, e is the charge of the electron, k is Coulomb's constant, and z is the atom's atomic number. It is assumed here that the mass of the nucleus is much larger than the electron mass. This equation determines the electron's speed at any radius. It also determines the electron's total energy at any radius. The total energy is negative and inversely proportional to r. This means that it takes energy to pull the orbiting electron away from the proton. For infinite values of r, the energy is zero, corresponding to a motionless electron infinitely far from the proton. The total energy is half the potential energy, which is also true for non-circular orbits by the virial theorem, a quantum rule. The angular momentum L equals mEVr is an integer multiple of h. Substituting the expression for the velocity gives an equation for r in terms of n, so that the allowed orbit radius at any n is the smallest possible value of r in the hydrogen atom is called the Bohr radius and is equal to the energy of the nth level for any atom is determined by the radius and quantum number. An electron in the lowest energy level of hydrogen therefore has about 13.6 electron volts less energy than a motionless electron infinitely far from the nucleus. The next energy level is minus 3.4 electron volts. The third is minus 1.51 electron volts, and so on. For larger values of n, these are also the binding energies of a highly excited atom with one electron in a large circular orbit around the rest of the atom. The hydrogen formula also coincides with the Wallace product. The combination of natural constants in the energy formula is called the Rydberg energy. This expression is clarified by interpreting it in combinations that form more natural units. Is the rest mass energy of the electron is the fine structure constant. Since this derivation is with the assumption that the nucleus is orbited by one electron, we can generalize this result by letting the nucleus have a charge q equals Ze, where Z is the atomic number. This will now give us energy levels for hydrogenic atoms, which can serve as a rough order of magnitude approximation of the actual energy levels. So for nuclei with Z protons, the energy levels are. The actual energy levels cannot be solved analytically for more than one electron because the electrons are not only affected by the nucleus but also interact with each other via the Coulomb force. When Z equals 1 alpha, the motion becomes highly relativistic, and Z2 cancels the alpha 2 and r. The orbit energy begins to be comparable to rest energy. Sufficiently large nuclei, if they were stable, would reduce their charge by creating a bound electron from the vacuum, ejecting the positron to infinity. This is the theoretical phenomenon of electromagnetic charge screening, which predicts a maximum nuclear charge. Emission of such positrons has been observed in the collisions of heavy ions to create temporary superheavy nuclei. The Bohr formula properly uses the reduced mass of electron and proton in all situations, instead of the mass of the electron. However, these numbers are very nearly the same, due to the much larger mass of the proton, about 1836.1 times the mass of the electron. So that the reduced mass in the system is the mass of the electron multiplied by the constant at 1836.1 equals 0.99946. This fact was historically important in convincing Rutherford of the importance of Bohr's model, for it explained the fact that the frequencies of lines in the spectra for singly ionized helium do not differ from those of hydrogen by a factor of exactly 4. But rather by 4 times the ratio of the reduced mass for the hydrogen versus the helium systems, which was much closer to the experimental ratio than exactly 4. For positronium, the formula uses the reduced mass also, but in this case, it is exactly the electron mass divided by 2. For any value of the radius, the electron and the positron are each moving at half the speed around their common center of mass, and each has only 1/4 the kinetic energy. The total kinetic energy is half what it would be for a single electron moving around a heavy nucleus. Red Berg Formula. The Red Berg Formula, which was known empirically before Bohr's formula, is seen in Bohr's theory as describing the energies of transitions or quantum jumps between one-orbital energy levels. Bohr's formula gives the numerical value of the already known and measured Rydberg's constant, but in terms of more fundamental constants of nature, including the electron's charge and Planck's constant. When the electron gets moved from its original energy level to a higher one, it then jumps back each level until it comes to the original position, which results in a photon being emitted. Using the derived formula for the different energy levels of hydrogen, one may determine the wavelengths of light that a hydrogen atom can emit. The energy of a photon emitted by a hydrogen atom is given by the difference of two hydrogen energy levels, where NF is the final energy level, and Ni is the initial energy level. Since the energy of a photon is the wavelength of the photon given off is given by this is known as the Rydberg formula, and the Rydberg constant R is, or in natural units. This formula was known in the 19th century to scientists studying spectroscopy, but there was no theoretical explanation for this form or a theoretical prediction for the value of R until Bohr. In fact, Bohr's derivation of the Rydberg constant, as well as the concomitant agreement of Bohr's formula with experimentally observed spectral lines of the Lyman and pattern. This was established empirically before Bohr presented his model, shell model of heavier atoms. Bohr extended the model of hydrogen to give an approximate model for heavier atoms. This gave a physical picture that reproduced many known atomic properties for the first time. Heavier atoms have more protons in the nucleus, and more electrons to cancel the charge. Bohr's idea was that each discrete orbit could only hold a certain number of electrons. After that orbit is full, the next level would have to be used. This gives the atom a shell structure, in which each shell corresponds to a Bohr orbit. This model is even more approximate than the model of hydrogen, because it treats the electrons in each shell as non-interacting. But the repulsions of electrons are taken into account somewhat by the phenomenon of screening. The electrons in outer orbits do not only orbit the nucleus, but they also move around the inner electrons. So the effective charge Z that they feel is reduced by the number of the electrons in the inner orbit. For example, the lithium atom has 2 electrons in the lowest 1s orbit, and these orbit at Z equals 2. Each one sees the nuclear charge of Z equals 3 minus the screening effect of the other, which crudely reduces the nuclear charge by 1 unit. This means that the innermost electrons orbit at approximately 1/4 the Bohr radius. The outermost electron in lithium orbits at roughly Z equals 1, since the 2 inner electrons reduce the nuclear charge by 2. This outer electron should be at nearly 1 Bohr radius from the nucleus, because the electrons strongly repel each other. The effective charge description is very approximate. The effective charge Z doesn't usually come out to be an integer, but Moseley's law experimentally probes the innermost pair of electrons, and shows that they do see a nuclear charge of approximately Z-1, while the outermost electron in an atom or ion with only 1 electron in the outermost shell orbits a core with effective charge Z-K, where K is the total number of electrons in the inner shells. The shell model was able to qualitatively explain many of the mysterious properties of atoms which became codified in the late 19th century in the periodic table of the elements. One property was the size of atoms, which could be determined approximately by measuring the viscosity of gases and density of pure crystalline solids. Atoms tend to get smaller toward the right in the periodic table, and become much larger at the next line of the table. Atoms to the right of the table tend to gain electrons, while atoms to the left tend to lose them. Every element on the last column of the table is chemically inert. In the shell model, this phenomenon is explained by shell filling. Successive atoms become smaller because they are filling orbits of the same size, until the orbit is full, at which point the next atom in the table has a loosely bound outer electron, causing it to expand. The first Bohr orbit is filled when it has 2 electrons, which explains why helium is inert. The second orbit allows 8 electrons, and when it is full the atom is neon, again inert. The third orbital contains 8 again, except that in the more correct Sommerfeld treatment there are extra d electrons. The third orbit may hold an extra 10 d electrons, but these positions are not filled until a few more orbitals from the next level are filled. The irregular filling pattern is an effect of interactions between electrons, which are not taken into account in either the Bohr or Sommerfeld models and which are difficult to calculate even in the modern treatment.